method, here the coefficient of the slack and the surplus variable becomes 0. So here I hope all of you have understood how to bring the given LPP into standard format, then satisfying the condition by using the slack of surplus variables and bringing into the format which is now attemptable to find a solution. So here the table is also a bit modified from the one that we have discussed earlier. Here the ratio column is eliminated from in the dual simplex method. So instead of ratio column, we're gonna make the ratio as a row here in this particular case. With this little modification, I'm going to teach you how exactly the solution is to be arrived at by using the dual simplex method. Here the basic variable column remains the same, CBO remains the same, CO remains the same, and we have introduced the variables here. X1, X2 are the variables that is there in the question, and S1 and S2 are the slack variables that we have, and then we have a constants column. So I'm going to fill up the cells above the variables by using the values that is available there in the objective function. So therefore coefficient of x1 in the objective function is -6, coefficient of x2 in the objective function is -1, coefficient of s1 in the objective function is 0, coefficient of s2 in the objective function is 0. Here we do not write anything. So we have written the first set of primary table. Now the first set of variables or the basic variables that needs to be evaluated for their existence in the solutions are the slack variables. Since we do not have any surplus variables, neither the artificial variable in the dual simplex method, we only have slack variables. So therefore we're going to take these slack variables s1, s2. I'm going to write the z equation, and I'm going to write one more row called as ratio. So this is the fundamental difference in the structure of the table that we have from simplex method and the dual simplex method. Okay, so the coefficient of the basic variables that we have now selected in the objective function are 0 and 0, and here we do not write anything. So the first set of table needs to be filled out by using the given constraint that we already have. So here therefore I'm going to, just as in the case of simplex method, I'm going to use the coefficients of the variables in the constraints to fill up these cells. So -2 from here in the first constraint, -1 of the x2, s1 is 0, sorry, s1 is there in the first constraint, s2 is 0, so the constant is -3. Next is the second constraint. Okay, so this ends the values that we have actually filled out by using the system of equation that was given earlier. Now we are going to find out the z equation values just by using the relation that we have got used to while calculating the z equation elements in the simplex method as well as in the bigger method. Since I know the values, I'm going to simply write it as, so I'll repeat once again. Z equation element that needs to be written here is 0 into -2 plus 0 into -1 -4 -6. So therefore it becomes 6 here. Okay, I forgot one thing. Before I get into finding the z equation elements, just as it is, we are supposed to find out the leaving row. As I've already told you, leaving row is basically found out as the most negative element among the RHS. So therefore here we only have two rows, and out of them we only have one value with one RHS with the negative value. So therefore I'm going to make this particular row as the leaving row. Okay, I'll repeat once again. Leaving row is among the RHS, regardless of how many equations that we have, is the row which consists of the most negative element among the RHS. So moving on, I'm going to write the z equation elements. Here we do not have any calculations. Okay, now the second modification that we have, or the deviation that we have from simplex and the bigger method to dual simplex method, is calculation of the ratio. Here the ratio is calculated as the z equation element divided by the corresponding leaving row element. So here 6 is the z equation element that we have, and the corresponding leaving row element here is -2. So therefore 6 divided by -2 will give you -3. Similarly, -1, 0 and 0. Now by using the ratios we are supposed to identify the entering column. So as I have already told you, entering column is basically identified as the least negative element in the ratio. So here least negative element in this area. So here we have ratios that we have already calculated as minus 3, minus 1, 0 and 0. So 0 and 0 will not to be considered. So among minus 3 and minus 1, the value which is least possible with a negative sign is minus 1. So therefore I'm gonna note this particular thing down and called as the entering column. So this ends the first iteration. Now we need to make the second set of table here by replacing s1 by x2. So therefore x2 I'm going to write it as and call it as knee pivot element, just as in the case of simplex method. S2 is still there in the iteration. Z equation remains in the calculation, and ratio that needs to be found out for this iteration also. Okay, see, coefficient of x2 in the objective function, coefficient of x2 in the objective function is minus 1, s2 is 0, z equation we need to find out afterwards. So just as in the case of simplex and bigger method, the first set of values in the second table, that needs to be filled up are the knee pivot elements. We use the same relation for finding out the knee pivot element, that is old element divided by the key element. Key element is the element which is at the intersection of the leaving row and the entering column, so which is minus 1 here in this particular case. So therefore knee pivot element for this particular position, that is minus 2 is the old element that we had and the minus 1 is the key element. So therefore minus 2 divided by minus 1 will become the first value of the first cell that needs to be filled up here. So therefore it becomes 2, this becomes 1, this becomes minus 1, this is 0, and RHS is 3. Okay, similarly the other elements are found out by using the relation that we had used earlier in simplex and bigger method. All other elements is equal to old element minus, open the bracket, entering column coefficients minus multiplied by the new pivot element. So I've already done the calculation. So therefore minus 3 comes here, 0 comes here, 1 and this becomes minus 3. Now we have completed the calculation of this new pivot element and all the other elements also. Now before we calculate the z equation elements, by using the ratio, the constant that we have, the one we need to identify the leaving row. So this becomes the leaving row because this is the only row that that has negative value among the constants. So then we need to find out the z equation elements just as in the previous case. So therefore it becomes 4, 0, 1 and 0. Then again the ratios as z equation element divided by the leaving row element. So it becomes minus 4 by 3, 0, 1 and 0. So this ends the second iteration. Okay. Now we need to identify which is the entering column from the second table. So therefore here we have only one negative value. So I'm going to make this particular, note this particular thing, column as the entering column. So x2 remains in the table as it is. S2 is now replaced by x1. So therefore x1 becomes the new pivot element. Z equation and the ratios. Coefficient of x2 from the objective function is minus 1, x1 is minus 6, and we need to do the rest of the calculation as it is, as we have done before. So since I have already done the calculation, I'm gonna write them as 0, 1, minus 1 by 3, 2 by 3, this is 1, 1, 0, minus 1 by 3, minus 1 by 3, and this is 1. As you can observe now, since we do not have any negative values in the RHS, the first condition that is mentioned here in order to declare that we have reached the solution stage is RHS should be greater than or equal to 0. So as we can observe from the third table here, RHS is greater than or equal to 0. So we need to calculate the z equation value elements also. So just by using the procedure that we have used earlier, 7 by 3, 4 by 3, and all the z equation elements, just as we have written down earlier, saying that, like, in order to declare a particular problem has that we have reached the solution stage, z equation elements are also supposed to be greater than or equal to 0. So here if we check 0, 0, 7 by 3 and 4 by 3, z equation elements are also greater than 0. So therefore we have reached the solution stage, and the solution is x1 is equal to 1 and x2 is equal to 1, and we need to substitute in the objective function to get whatever value that we basically get. Now note that if we have RHS as positives here, and if we end up having any negative elements here, then the solution is declared to be infeasible. I'll repeat once again, if we have the RHS as all the RHS are arrived as positive values, and if we end up having any negative elements in the z equation, then we say that we have reached the solution stage, but the solution is infeasible. So this is the procedure that is basically used to find a solution for an LPP by using the dual simplex method. I request all of you to make a note of a few questions and practice all of these methods rigorously.